Okay, today we are talking about logistic regression. Logistic regression is actually one of the most useful types of regression. It actually came about because there was a problem with using normal regression. But what happens is, in our end of the woods, in the social sciences, we actually have dependent variables that very often require something like logistic regression. A little history. In the old days, they used to use something called probit analysis. P-R-O-B-I-T. And that's really good. There's nothing wrong with it. It's just as good as logistic regression. But the trends, just like fashion trends, moved a bit away from probit analysis and in the direction of logistic regression when using these types of dependent variables. So we're going to talk about logistic regression. It's probably the only thing you'll ever need. Probit, if you ever run into it, is very similar and just as useful and really cool. But logistic regression is really the one you're probably going to use in graduate school and in all of your applied work. Just, I want you to know that that probit thing, you'll see it in a lot of older articles, and occasionally you'll see someone using it today. And you'll just know that it's very similar to logistic regression. So let's talk about why we want to use logistic regression. When we used regular regression, what we had was an x variable and a y variable. And the basic idea behind using logistic regression is that this normal construction that we have doesn't really work for certain variables, because with the normal variables that we've been working with, you can have any value you want on the x side, and, like a feeling thermometer, any value you want on the y side. So you can have values that go up and down all over the place. And you have scatter plots of a data cloud that looks like that, and your regression line looks sort of like that, and it works. Trouble is, what if you have a dependent variable that is binary? That means that it only has two choices. For example, did they vote for Carter or did they vote for Reagan in 1980? So you don't have all of this variation in y. You have only two options. So look what happens if you use a regular regression with something like that. Let's say we code Carter down here as a 0, and we code voting for Reagan up here as a 1. This is for your y variable. Now, let's have income being the independent variable. So if we have income being the independent variable, let's say lower income people voted more for Carter, and higher income people voted more for Reagan. So when your people have lower income, you're going to have a whole bunch. I mean, for every person, you find their income, so you'll have an income value for each person, but they're all going to be lined up right here. And then when you get to the Reagan people, richer people, they're all going to be lined up over here. Now that's what our scatter plot looks like. Now that's not okay, because look what happens. You put a regular regression line through that, you have that form. That's a linear form. So you're going to do this. You're going to have a line going through data that looks like that. Now, one of the issues associated with doing regression is that the error should be normally distributed around the prediction line. You shouldn't have what's called a pattern around the regression line. For example, you shouldn't have something that they like to call heteroskedasticity, which is a clear pattern, various different types of patterns around the regression line. And in this case, look what happens. All of the residuals form a very clear pattern around that regression line. And here we have the residuals following a very clear pattern along that regression line. So on the level of where the error term is going, it's not good. It's supposed to be scattered evenly around the regression line, but that's not scattered evenly at all. It's a triangle here, a triangle there, a triangle, triangle. That's not good. The second thing that's not good with it is when we have a regression line like this, our y hat is supposed to predict the value of your dependent variable. That's the whole reason for doing that. We want to know what somebody's predicted value would be, because our regression line is supposed to be better than the mean in terms of predicting something. That's why we did a regression line in the first place. So what about our predicting values? Well, look at what's happening. We're predicting all types of values between here and here, between 0 and 1 on the vertical axis. All types of values that don't exist, that cannot exist. Moreover, we have impossible values down here as well. We have negative values that we're predicting, and we have values here above 1. So in reality, in theory, none of our predictions are going to be very good because the regression line can't go where the data are. The data are flat over here and flat over here. And there aren't any scattered elsewhere, and there's none below that and none above that. So what we would like is a better regression line. One that will go where the data are and not go where the data are. So, and not go where the data are not. So what we would like to do is to have a logistic regression line, and that solves this problem. So for a logistic regression line, I am going to cut to the chase and show you what it looks like, and then I'm going to show you why it looks like that. So what we have here is a lot of data here and a lot of data here. A logistic regression line produces what's called an S-shaped curve. And the S-shaped curve looks like this. It hovers around down here where the data are near the 0. And then when it gets time to go up high where the data are near 1, it leaps really quickly up here and then hangs around up here where that is. Moreover, what we're going to be able to do is to reinterpret the meaning of this logistic line, because the logistic line, it looks like it has values here that are impossible, but they're going to become possible because instead of actually predicting the actual vote, we got a cool trick. We're going to predict the probability of voting for somebody. So we're going to talk about the probability of voting for Carter or Reagan, and that's going to be any number between 0 and 1. And as income increases, the probability will go up. Does it make sense? So it's all going to be kosher. It's all going to be perfectly okay. So let's talk about how we're actually going to do that. How are we going to get an equation that goes like that? Well, my son, who is a junior here at Emory now, loves to go fishing. Has a special fishing spot. It's really good. He's got a chance of catching a good fish in that spot. 2 times out of every 3 he goes. That's right. That means if he goes 3 different times, he'll miss once, but he'll get twice a good fish, and there'll be a big fish roast. Okay? Otherwise, we're vegetarian. It's the only thing we do otherwise. Otherwise, there's a fish. But otherwise, nonetheless, that wide-mouthed bass or whatever gets eaten for dinner. Okay? Now, what we're talking about now is the odds of success. Now, what we've been talking about in the whole course is probabilities of things happening. But now we're going to switch it to gambling. So when you actually go to the bookie, which you're not supposed to do, but if you did go to the bookie, you're going to be looking at the odds of making it big. So you're going to be talking about the odds of winning the lottery. If you look at the back of the lottery ticket, you fill out the lottery ticket, you mark in all the things, and you look at the back of it, it says the odds of your winning. They're not telling you the probability of your winning, they're telling you the odds. So this odds thing is something similar to probability, but it's also a little bit different. So what do we talk about a success? The success is every time my son catches a fish. Something that's not a success is every time he goes fishing but doesn't catch a fish. He goes fishing 3 times, twice he catches a fish, once he doesn't catch a fish. So let's not talk about probability. Let's talk about the odds, which is another way of talking about the same type of concept, the likelihood of something happening. Well, what we're going to talk about is what are the odds? So what are the odds of that thing working? And then we'll actually tell you how the relationship is exactly between odds and probability. But let's just talk like a bookie would talk. And what's the odds of actually having that thing happen? Well, what we want to know is when you're talking about probability, you're talking about the probability of you catching the fish based on all the times that you went fishing. So if you went 3 times and you caught a fish twice, you're dividing 2 by 3, right? But with odds, we're not doing that because we're not interested in dividing by all the times. We want to know what the odds are, meaning what is the chances of succeeding, not based on the total number of times we went, but based on the times that we didn't succeed. So we want to know what are the odds of, what is the chances of winning relative to the chances of not winning. So what we want to do is say, okay, how many times did he go fishing and catch a fish? 2 times. How many times did he go fishing and not catch a fish? 1 time. So what we're going to do is we are going to divide the success by the failure. The success by the failure. In fact, we could actually do it in terms of writing the probability of success over the probability of the failures, or the numbers of successes divided by the numbers of failures. So, what are the odds of him catching a fish? 2 to 1. That's how you'd say it. That's not how you'd say the probability. The probability would be 2/3. You're dividing by 3. But if you're talking about the odds of my son catching a fish at his favorite watering hole, it's the successes divided by the failures. Does everybody understand? You're dividing by a different number. Same idea, but it's relative to something different. The successes relative to the failures. So this division is called the odds ratio. The odds ratio. Well, this odds ratio, in this case, is 2 to 1, or 2. He's got twice as good a chance of catching a fish at his favorite watering hole as he does of not catching a fish. Well, that's actually very useful because what we're going to end up doing is taking the log, the natural log of that odds ratio. And we're going to get something out of it that we are going to be really surprised by. Watch this. Now, I'm going to be referring to 2 things. If you go to your book on page 235 and 236 of Agresti and Finlay, 235 and 236, you get a really nice description of the odds ratio. So mostly we talk about probabilities, but when you talk gambling, you like to talk sometimes odds. And so you get a nice description of that on 235 and 236. Now we're going to leap over to page 484 of Agresti and Finlay, where they actually start talking about the logistic regression approach. So what we're going to do is the following. We're going to take that odds ratio and we're going to write it this way. The probability of success over the probability of failure. Now, I'm talking probabilities now. So how does that compare to this? It's the same thing. Because look what happens. What's the probability of success? You would have divided by the total number of times he went, right? So this would have been divided by 3. And the probability of failure? You would have divided that by 3. The thirds cancel and you just get 2 over 1. Okay? So this is the same thing. If the probability of success is p, the probability of failure is 1 minus p. And that's exactly the same as the odds ratio that we just had. Okay? Now, what we want to do is we want to take, and we're using ln instead of log, we want to take the natural log of that. And the reason we want to take the natural log is we're going to exponentiate some things, and it's going to turn out to be a very nice algebra. So let's actually do that. Let's clear this off. And let's go the ln of p over 1 minus p. We're going to say that that is equal to beta x. Now, for the first time in the course, I'm going to be referring to beta x as a vector of betas and a vector of x's. And that vector of betas will also include the intercept. So this is not just the intercept. This is the intercept and all of the other slopes. And this x here is a vector of x's, which is all of the other independent variables. So this would be equivalent to beta naught plus beta 1 x1 plus beta 2 x2 and so on. But to make it more convenient so that I can just write beta x rather than all that jazz, I'm just going to use the matrix notation rather than all that jazz. But it means the same thing. Are we okay with that? Okay, so let's get rid of that and make it simple that way. Now I want to exponentiate both sides. If I take the exponent of both sides, take this, make the exponent of that, e to this power and e to that power, the log is the inverse of exponentiation, so they are like matter and antimatter. They annihilate one another. So what you're going to get here is just p over 1 minus p. And over here, you're going to have the e of beta x. So you have the exponentiation left here, but on this side, the exponentiation simply got rid of the natural log. So this natural log of this p is actually going to be our dependent variable. And this, all the betas, are going to be our normal independent variables. Our right-hand side is not going to change. It's just that our left-hand side is going to be p over 1 minus p, the log of it. So this is going to be our new independent variable. This, by the way, is going to be called the logit. That's going to be our new dependent variable, and that dependent variable is going to be called the logit for short, which is the log of the odds ratio. The log of the odds ratio. Okay? So we've done this. We've exponentiated both sides, and now we're going to isolate this p. So we have p is equal to e to the bx times 1 minus p. So I just multiplied 1 minus p on both sides. Now I'm going to multiply through these, the beta x here. I'm going to multiply through the brackets here. So we're going to have p equals e to the beta x minus e to the beta x times p. So I multiplied e to the beta x through the brackets, and I got that. Now I want to take this term that has a p in it and throw it on the other side. So I have p plus e to the beta x. P equals e to the beta x. And now I want to factor out this p. So I have a p times 1 plus e to the beta x equals e to the beta x. And now I want to divide by 1 plus e to the beta x so that I isolate my p. So p is going to equal e to the beta x divided by 1 plus e to the beta x. Now we're actually done, except that this is not the way it's normally presented. It's normally not presented in this exact form, although this form is the one I'm going to use to explain how the algebra actually works. But normally what they do when they get to this stage, they add another step and they go e to the beta x divided by 1 plus e to the beta x. And then they multiply top and bottom by e to the negative beta x divided by e to the negative beta x. And the reason they do that is typically they don't like two of these e to the beta x's floating around in the same equation, which is perfectly okay as far as I'm concerned, but a lot of people don't like that. And so what this does is this will cancel with this. So on the numerator, you'll only get a 1. And for the denominator, this will multiply through, and when the e to the negative beta x hits the e to the beta x, you'll get the number 1. Okay? And then you'll get plus e to the negative beta x. Okay, so e to the negative beta x times e to the beta x will give you this 1, and otherwise when you multiply this times that 1, you'll get that e to the negative beta x, e to the negative beta x. And that's the form that you normally see. But again, we're going to go back to this one right here, which is with the 2 e to the beta x's. And p, of course, remember that is the probability of the event. And we're going to have x here and y here. And it goes from 0 to 1. And we're going to be looking for something like that. So let's talk about what we've actually done here. You see, when we have this form right here, what happens when this right-hand side of the equation, your intercept and all of the independent variables with all of their slopes, what happens when that goes towards 0, when it gets down to 0? Well, 0 divided by anything is 0. So when this thing gets towards 0, the probability, the lowest you can get, is 0. What happens when e to the beta x becomes really big? You're predicting huge numbers. So let's predict something really ridiculous. Just imagine how big it would be, like close to infinity. You get a huge number on the top in the numerator, and a huge number on the denominator, and the 1, you can just ignore that because you're dealing with such a large number for e to the beta x. So you're getting a large number divided by a large number, and this is asymptotically approaching the number 1. So this p follows the classic rules of probability. It goes between 0 and 1. So what we have is when we use the logit, or this thing here, the log of the odds ratio, for your dependent variable, you actually have a linear line. And the linear line will work with this. But this is the key. When you're doing the regression, what good is this right-hand side? Because what is it predicting? Is it predicting anything that's useful to you? No, it's not predicting anything that's useful whatsoever. It's predicting this guy. The logit, which is the log of the odds ratio. If you ever go up to somebody and say, hey, look, I got a great thing for you. This is my prediction of the log of the odds ratio. Do you think they're going to give you 10 cents or even a cup of coffee? I mean, they don't care about the log of the odds ratio. It's useless. What they care about is p. They want to know the probability of success. They don't want to know about the log of the odds ratio. But the log of the odds ratio did get rid of the problem of having that weird predictor line, because now we have a linear predictor line. But what we want is p. We don't want a linear predicting line of something that doesn't make sense to us. We want p. So how do we get p? Well, this may give us a linear line, the log of the odds ratio, but if we transform that to get our p's by simply exponentiating what we have here, we can solve for our p's. Our p's is this. Or actually, our p is this. This is our p, which is the 1 over 1 plus e to the negative beta x. Or you can use this version over here. P, that's what we want. So once we have our vector of slopes and variables, we just take that entire right-hand side, exponentiate it, divide it by 1 plus the same thing, and we've got our p. We've got our predicted value. And that's what we want. We want to know the probability of something succeeded. So once we get our right-hand side, we have to transform it to get our p. And when we do that, our p will produce that S-shaped curve. And that's what we wanted. So logistic regression is all about getting a p. It's not about getting a L, it's not about getting the log of the odds ratio, it's about getting a p, and we want that p to follow this S-shaped curve, and it does. That's the key. That's the key. Now, the very first article I ever published was in the American Political Science Review, which was which is the leading journal in political science, and it dealt with a logistic regression that I thought was really cool. And but you know, always trying new things. This is in the days before you had the modern graphing stuff. We had a Hewlett-Packard plotter back then connected to a computer that was way slower than your wristwatch, let alone your cell phone. And so that plotter nonetheless worked all weekend and produced three-dimensional plots of these logistic curves. And back in those days, you had to take whatever plots you had and you had to give them to a graphic artist who redrew them with Indian ink. That's what graphic artists used to get paid for. Funniest thing was my logistic curve had so many, it had a warped three-dimensional curve coming out of there, and I had like 6 of those plots. The graphic artist just about quit. He wrote a nasty note afterwards saying, "I don't care how much I get paid for, you had too many lines on this thing." Little did he know that the future of graphic arts was going to have a lot more lines than that. Anyway, so these logistic curves produce nonlinear lines. They produce nonlinear lines, curvy lines that are really cool, really sexy. You want those things in your paper. I mean, they're really nice to look at, especially the 3D ones, which can print out really nicely. So now this gets us to assignment, actually I believe it's assignment 9. Okay? Now, finding good discussions of logistic regression is not so easy. So our book actually has a very good discussion of logistic regression, so I actually like that. But if you want another version actually that talks about it with R, probably the best way to get it is to get it in John Fox and Sanford Weisberg's book, a really great book, which is an R companion to applied regression. And if you click on that link, which I have right here, our assignment 9, you will actually be transported over to Amazon and you will get it. And there's a special spot on page 235 to 237 that really summarizes the output for R and explains it in terms of logistic regression. That's just perfect. And we're going to go through that in just a minute. All right, so just for class discussion, and you can get the book to get the entire thing. We're talking about John Fox's and Sanford Weisberg's book on those pages. So let's actually look at what they're talking about here. They have a data set that they use, fascinating discussion that they have, and they have a variable that is binary, and they're interested in, that means only 2 values to it, and they're interested in using logistic regression for that variable. Okay? Now, we're going to actually get the exact same R output that they get here, but let me just explain what they're going after. They have the actual call for the model, logistic call for the model. They have the output, which looks a lot like the normal regression output. One thing you should know is that you're using Z values here rather than T values. I'll explain that in a little bit. But you're basically using the same Z table. And you'll notice that your normal means for fit, such as the R square, are not there, but they have a couple other things that they have over here, including something that they call the AIC. So these outputs are for the normal independent variables and the normal intercept, but again, those are things that are for the log of the odds ratio, so just by themselves they're not as useful as we would want. So how are we going to actually use these things? What would be a nice way to actually put these things into actual use? I want to actually read to you how they actually go about using them. All right. Here they have the log of the odds ratio equaling the right-hand side, exponentiating both sides. They get the exponentiation of all of those things, all of the exponentiation of the intercept. Now these originally are pluses between the variables, so once you exponentiate, you're going to get times. And you'll get the log for the log of the odds ratio going away. and you'll just have the odds ratio, okay? And so this is giving you what's called the fitted odds of success. That is the fitted probability of success divided by the probability of failure. The exponentiation of the model removes the logarithms and changes it from a model that is additive in the log odds scale to one that is multiplicative in the odds scale, simply because you exponentiated it. Okay, because when you when you have exponents and you're adding things, that is equivalent to multiplying the exponents, okay? For example, increasing the age of a woman by 1 year, holding the other predictors constant, multiplies the odds of her being in the workforce by, and that was the third variable, and the third estimate by the exponentiation of negative 0.06, or 0.931. So let's take a look at what they got here for their actual slope. So you see what they have here is age. Did everyone see the estimate here? Negative 0.06287 is for the logistic regression. They got the age slope. So they're taking that age slope exponentiating it and getting this number right here. Now what does that number mean? 0.9391. That means it's a number less than 1. That means that the chances for, based on 1 year increase, it reduces the odds of her working by 6%, meaning there's a 93% chance of her working based on a year increase in that of her age. So that 6% decrease, of course, is 1 minus the 0.9391. So the exponents of the coefficient estimates are called risk factors. And the exponents, or the odds ratios, and they can be viewed all at once. Now that's what we're going to be doing. You see, these are the risk factors. Now for age, that means for 1 year increase in that independent variable, which was age, there's a 94% chance of that person, in this case, for the dependent variable, which is probability of working, there's a 94% chance of them working. That means there's a 6% chance of them not working. That 94 is less than 1. So these estimates are after exponentiating each one of those individual slopes based on a 1 unit increase in the independent variable. 1 times anything is just that thing, so they're exponentiating just a slope. So these are really valuable to know. Now, for this variable, look at this value here, is 2.24. 1 unit increase in that, hey, the person is more than twice as likely to have to be employed, or the probability of employment based on this data set they're using, that dependent variable. So anything less than 1, meaning 1 unit increase in that variable, means they're going to be less likely. Anything bigger than 1, they're going to be more likely. So this 2.24 means they're approximately twice as likely to be employed for that variable, 1 unit increase in that variable, and so on. Now, notice that we have these estimates here for whether they're likely or not likely, but we also have a confidence interval here. That confidence interval is spectacular, because what we have is a 95% confidence interval that these estimates here, or the risk factors, are between the lower number and the higher number. So we not only have the risk factors for each variable, but we have a confidence interval for those variables, for those estimates. That's how you work with logistic regression. It's the simplest way to do it. Now, when I work with logistic regression, I actually plot out the actual values of p, and I have these nonlinear plots that look really cool and interesting. So there are more than one way, there's more than one way to actually describe your results. But when you're dealing with survey results, just looking at these risk factors, just these numbers here, and looking at the numbers whether they're greater than or less than 1, is the easiest and most straightforward way. So you can look at the significance of your z-tests, and you look at the risk factors, and you're done. And you know which variables are the most significant, and what are the so-called risk factors, or the values, the importance of each value, of each factor based on 1 unit increase in those independent variables. Now let's use it for our own data set. Let's go to assignment 9. Now for this one, we don't have to have any special package added onto R, so we'll just be able to run it. I would like everybody to copy everything from the top to the bottom, paste it into Rstudio, and simply run it right now, and let's look at what happens. We don't have to change anything right now. All right, so all right, perfect. Did everyone get it to work? All right, now let's go back to the R code and let me explain it. First thing we're doing is simply getting my data from the panel 80 study that we've been using all along. The second thing we're doing is looking at the names, just like we've always done. And now we want to make a binary response variable. So we have a variable called vote. And vote has a value of 1 if they voted for Carter, and it has a value for 2 if they voted for Reagan. Now we want to change that. We want to change that so that if they voted for Carter, it's a 0, and if they voted for Reagan, it's a 1. So we want the values to be 0 and 1. That's our predicting values. So it comes in the survey as a 1 and a 2, and we want to change it to a 0 and 1. Now, since with this particular thing, Reagan is actually scored as a 1, and Carter is scored as a 2. So we don't want Reagan to be changed. We want the Carter to be changed. So we want the Carter to be a 0 and the Reagan to be left alone as a 1. Now there's a whole bunch of different ways to how to do that. I'm going to show you 2 different ways to do that. So the first thing I'm going to do is my subset data 1, which keeps only those people who voted for Carter and Reagan. There are a few people who voted for some of the other candidates, Anderson and so on. Then we're going to talk here about my subset data 2, which will start with my subset data 1, but we're going to select out only those variables that we're interested in using. And this is going to be a simple model. I'm going to have car field 3, ray field 3, income, age, party ID. It just keeps a few variables so that we don't have the whole kitchen sink floating around in there. And then I could have printed out my subset data 2, but I put a pound sign in front of that just because I said I did it once to see it, but we don't need to do it again. Occupies a lot of space. But if you ever do something like that, make sure you print it out at least once to see it, to make sure that the subset command worked as you were expecting it. Now, in vote, which is the variable we're using, a vote for Reagan equals 1 and a vote for Carter equals 2. We want to change that. Now there's going to be 2 ways we do it. The first is going to be using a loop, and I do it with a loop because I wanted to show you how a loop works so that you're not frightened of using them. And the second way I do it is just using a regular if-else statement. So they get the exact same result, but let's take a look. So in this one, I needed to initialize some type of variable called binary vote, and that's going to be our dependent variable. So what we have is binary vote here. I just set it equal to 0, and now I'm going to recode it, okay? For, which is the loop, and for starts a loop. It goes between these squiggly brackets, 2 squiggly brackets, and I've got only 1 line in there. For I, which is the counter variable, in 1, 2, the number of rows in my subset data 2. So this is a nice way of doing something a certain number of times for every observation in a data set. I simply say from 1 colon 2, how many times is how many rows, the number of rows in the data set. So this n row simply says, how many people are there in that data set? Count the number of rows. So let's say there's 700 people, 1 to 700. Do this, everything between the squiggly brackets, 700 times. 1 to 700, meaning go through each row and do this. And then what is it that you're doing? Well, if my subset data $vote, notice I have to have square brackets after the vote with the counter I in front of it, because I'm not talking about just the whole vector vote. I'm talking about each individual observation. So you have to use the square brackets to tell R that you're looking at each person. And the I is the counter. So you go to row 1, and that's Tom. So you go to my subset data $vote, you look at Tom's spot, and you look to see if that person has got a 2 or a 1. Did they vote for Carter or Reagan? All right? So if it's a 2, then I want to change that 2 to a 0. Then, so it's if this condition is satisfied, which is they voted for Carter, then you just write binary vote for that same person with the I there, with the square brackets, equals 0. Else binary vote for the same person equals 1. So this is an if-else statement with the if and the else separated. So it goes through every single row, and it says if they voted for Carter, then make this the value for binary vote equal to 0. Otherwise, make it equal to 1. End of square bracket, we're done. So that's how to do it with the loop. Now, how do you do it with sort of a simple line without the loop? Well, you can use an if-else statement, and this is just for managing data. It's if an if-else statement is not separated, if and then separated that with the else. It's an if-else combined statement, and I'm going to call this binary vote 2. And the reason I'm calling this binary vote 2, so I don't confuse it with the first binary vote. And so all I say is binary vote 2 equals, which is the less than followed by a dash, and then the statement if else. And the if else statement says, look at this condition, my subset data 2 $vote, meaning the vote in that data set. If that equals 1, then, and then there's a comma here, 1, 0. So if this is satisfied, if the first condition is satisfied, then make it equal to a 1. Otherwise, make it equal to a 0. So the if-else statement has a lot of language sort of built into it. So if-else means if this is satisfied, then make this binary vote 2 equal a 1. And it already knows that the second value over here, 0, is what happens if this thing is not satisfied. So this is a really short way. This is a way of doing it in a loop, and that's a way of doing it in one line. And so I create my subset data 3. And I column bind in 3 nice columns my subset data 2, which is all the variables in my subset data 2. Plus I put binary vote and binary vote 2. Binary vote used with this loop, and binary vote 2 used with the if-else statement, just so I can compare it and see. And then I printed out my subset data. So let's look. Let's look at what actually happened. Well, well, well. Here we have a 1. This person voted for Reagan. And look, their Ray field feelings is higher than their car field feelings, so that makes sense. Binary vote is a 1, and binary vote 2 is also a 1. So you see, this person voted for Carter, okay, and their binary vote is a 0, and binary vote 2 is a 0. So you see, binary vote and binary vote 2 get you the exact same thing. Different ways to do the same thing. All right? And again, the only reason I introduced that loop thing is just to introduce you to loops in R. Anyway, so now we have a dependent variable that we can use, this binary vote, which goes between 1 and 0. So now let's talk about how we actually get the logistic regression. And this will be quick because it's so simple. I'm going to call this logistic regression logit vote dot model. I could have called it Tom, Susie, anything, but if I call it the logit vote dot model, I'll remember. It's about voting, it's a logistic thing, and it's my model, okay? And that's going to equal less than followed by dash to GLM instead of LM. So instead of using the LM procedure, I'm using the GLM procedure. That's it. Now watch. GLM, I'm using the binary vote. I could have used binary vote 2 or binary vote. It doesn't matter. But I used binary vote is modeled as I have my normal set of independent variables. The only difference is that after I have my normal set of independent variables, I have a comma and I write family equals binomial. Now that binomial actually has a default value of the logistic, which simply says this is a binomial variable, so you have to use something like logistic. The default value is to use the logistic, is to create the logit. However, you could actually do other things, such as probe it and other things, but the default value is logistic, so that's fine. And then it has my data set. So the only thing is, I change my LM to a GLM, and I write family equals binomial, and I'm done. That'll give me my results once I do a summary. And now we want those individual risk factors. I round them off, okay? And I round them off to 2 decimal points. That's what that 2 is at the very end. And I exponentiate, I'm C-binding here, the actual estimate equals the coefficients of the logit vote dot model, and this will give me the confidence intervals for the logit vote dot model, and that will give us the actual results that we want. And now let's look at the output for R. We scroll all the way down past all of the people, and there's our results. And it's just like we had in the book. We have our normal stuff for the regression. We have our intercept, our variables here. These are the slopes, but these are for the log of the odds ratio. By themselves, they're not so useful. All right, and we have our fit measures that we can use over here. The Z values are used instead of our T values. And here we have our risk factors, right here. So, a 1 unit increase in party ID doubles the person's probability of voting for Reagan. Does everyone see here? Does you see how easy it is to interpret? You see this 2.08? Party ID, a 1 unit increase in person's party ID, meaning party ID goes from a low of strong Democrat to a high of strong Republican. A 1 unit increase, 1 notch up in party ID, doubles the probability that they're going to vote for Reagan. That's what that says. Okay? Age, a little bit, as you get a little bit older, there's a slight increase, not much. Income, slight increase. And then we have the 95% probability, the 95% confidence intervals for those risk factors. That's it for logistic regression, and that's how you interpret them. It's fascinating and easy to do. Couldn't be simpler. GLM instead of LM, and then the family statement, and you're done. And then you get all of that printed out, and you can just interpret it as simple as could be. So if some of you want to add a vote to your final paper, in addition to the stuff that you've been working on with card field 3 and ray field 3, you can now do it. Use your you use your exact same right-hand side. You put in your normal right-hand side, your normal equation. Copy and paste it from what you've been using all semester. Change it to a GLM instead of LM, and put your family in there for this statement right here. Family equals binomial, and you're done. And then you want to get you want to print out this right here, this risk factors. So you copy and paste that line as well so that you get those risk factors printed out because they make it so interpretable. Okay, any questions? It's a great thing. Logistic regression. It's a good thing to add. You not only have feeling thermometers going on, but you have the probability to vote. Covers all your bases.